Okay, in this video we shift our attention to the term structure of interest rates, and we'll be discussing things like the yield curve and also spot rates, which we'll be using to price bonds. And there will be some numerical aspects to this lesson or to this video as well. So let's start off with the first sort of phrase in this title, the term structure of interest rates, or the this is also known as the maturity structure of interest rates. What do we mean by that? Well, what we mean by that are the factors explaining the difference between yields that we generate on bonds with different times to maturity. Taking away factors like credit risk, which becomes higher potentially the longer the term to maturity, liquidity aspects, tax status, etc. What are the factors explaining why you earn a different yield on bonds with different times to maturity? And if you're trying to analyze the term structure of interest rates, making comparisons across different maturities, this is best done, so best analyzed, so to speak, using bonds with the same parameters, obviously the same parameters other than time to maturity, because you need bonds with different times to maturity to be able to make comparisons across different terms. So when we say same parameters, we mean things like currency, the same level of risk, credit risk or default risk, the same liquidity, the same coupon rates or similar coupon rates, the same tax status, the same, when you compute these things, these yields, the same periodicity assumption. Otherwise, if you compute under different periodicity assumptions, you're going to get different results for the YTM. We've done that. Now, I said it's best to analyze using bonds, but the absolute sort of best thing you can use, so this is a bigger best, is using yield to maturity, YTMs, on zero coupon bonds. If you can get your hands on a set of yields to maturity for zero coupon bonds, that's going to be the best thing, and preferably make them default risk free, meaning issued by a government, a developed market government. That would be the best thing you can get your hands on. The YTMs on zero coupon bonds, the yields to maturity on zero coupon bonds, will be effectively referred to as spot rates. And they're very convenient things because we can use spot rates to perform time value of money computations pertaining to single cash flows. You can use a spot rate to discount a single cash flow from to today's point on the timeline. So you've got a series of these zero coupon YTMs. You've got a series of spot rates, and you can build what's known as a spot curve, which is a graphical representation of the whole set of numbers. Spot curve, also known as a zero curve. It may also be known as a strip curve, because you can also construct these curves using YTMs, yields to maturity, on elements of stripped bonds, which I kind of talked about in a previous lesson. And the very nice thing about using zero coupon bonds, which is a big plus of them, is that there is absolutely no coupon reinvestment risk. You may remember, or not, that when I defined the yield to maturity a couple of videos ago, I said that the yield to maturity is only realized if you hold the bond to maturity, if you, all the cash flows are received on time and in full, yeah. But also if all the coupons that you receive in the meantime whilst holding the bond are reinvested at a rate equal to the YTM. Now, with zero coupon bonds, you don't have that risk. You don't have to reinvest the coupons because you get no coupons, so there is no coupon reinvestment risk, which is a good thing from the point of view of making using these rates. Right. Now, as a result, I said you get what's known as a spot curve or a zero curve, which is going to be a graphical depiction of the rates on a timeline. So here you've got the YTMs, the yields to maturity on those zero coupon bonds. Hopefully, if you can get your hands on these, and here you've got the time to maturity on the horizontal axis, and what you'll typically see is a curve that looks something like this. So the longer the time to maturity, the higher the yield that investors expect from it. And yeah, if you're using bonds, preferably from the same issuer, i.e. a single government, denominated in the same currency, enjoying the same level of liquidity when it comes to market trading, realistically, you should get a curve where the only reason why certain bonds attract more yield or generate more yield is that term structure of interest rates factor. That's going to be the only sort of the only factor left. However, let me just at this moment state that if the curve is upward sloping, we would describe that as being normal. However, you may also find a curve that the curve is sometimes downward sloping, which is not necessarily the normal thing for it to do. However, that does happen. It's typically not a good signal, as we'll be discussing later on. We call such a curve an inverted curve. So the top one here was normal, a normal curve, yield curve, or spot rate curve, or normal structure of interest rates, term structure of interest rates, and the other is inverted or downwards sloping, downward sloping versus upward sloping. Okay, let me just mention a few issues. You may be tested on these, why not? Issues in constructing a spot curve or a zero curve. The problem is, in theory you should be using zero coupon bonds, and in reality you typically don't get that many zero coupon bonds trading, especially government issued zero coupon bonds. So most government bonds actually pay coupons. There are ways to go around this. You can do something called bootstrapping, but it's a bit problematic. And on top of that, all their issues typically have lower liquidity, typically are less liquid than on-the-run securities, so the newly issued stuff. And as a result, well, not as a result, they may trade away from par value. If a bond was issued a long time ago, its coupon may be completely off where the coupon would be nowadays. So these things trade either at a premium or a discount to par value, which actually generates a lot of tax effects, which make these bonds difficult to compare, because in many places the tax status of capital gains, the difference between the price you pay on a bond and the price you receive in terms of face value, will be taxed using capital gains tax, which is different from interest tax. So these bonds become difficult to compare in terms of their yield generation because they attract different tax statuses. They have different tax status depending on where the investors are and where these bonds trade. So it just complicates life. What we do in practice, however, is we typically use so-called on-the-run treasury securities, so the most recently issued batch of securities, to help us build a spot curve. And we will typically have data on something like a 2-year bond, a 5-year bond or note, maybe a 10-year and something in between. But for everything else that's not covered by specific issues that are coming to the market pretty much right now, we will have to make judgments. So if you know this point is here, this point is here, this point in here is here, how would you judge the 7-year rate? Well, you would use some form of linear interpolation between the numbers that you've already got from the hard data. So we use on-the-run treasury securities and interpolate, in a linear way, often between points on the curve that you get from actual bond data between points on the curve. So constructing the curve is not necessarily very easy. And of course, over here you'll also have a segment for yields on instruments that are less than 1 year or maximum 1 year to maturity. So for periods up to and including 1 year, we will typically be using money market instrument yields, money market instrument rates. But here it's very essential to make sure that we convert to the same basis, the same periodicity as with the bonds. You can't put on the same curve yields to maturity coming from bonds and discount rates coming from money market instruments unless you do some form of unification. And this is something we discussed in a previous lesson. I showed you on money market yields how we convert to the same periodicity basis once you have an AOR, an add-on rate. Okay, now for the numerical bit of this lesson, we're going to do some bond pricing using spot rates and trying to learn something and draw some conclusions concerning the yield to maturity, among other things. Bond pricing using spot rates. I said that spot rates are great for discounting single cash flows. Well, a bond essentially is a collection of cash flows, isn't it? A bond is a grouping of promised cash flows, that should come in the future. So over here we've got the following sequence of spot rates: 1 year, 2 year, 3 years, 6, 12, and respectively, accordingly 13%. And we're asked for the price per 100 of par value of a 9% annual coupon bond with 3 years to maturity. What is it closest to? Well, if you've got a bond with a 9% coupon and you're asked to compute its price or value per 100 of par, let's begin with a classic timeline. So that's my time axis. This is today, the point at which I'm doing the valuation. End of year 1, end of year 2, end of year 3. 3 is the maturity date. It was in fact after all a 3-year instrument. And because it's got a 9% coupon, I'm going to say it generates 9 here, 9 over here, and a much bigger 109 over there. Now, what we could do, or what we should do, is actually use these individual spot rates to discount each of the individual cash flows. So 6, 12, and 13, starting with the year 1 cash flow, the way you would discount it down to its PV, its present value, is by doing divide by 1 plus the discount rate. So that's 1.06 raised to the power of 1, of course, so just divide by 1.06. Now you do something similar to the second cash flow, but this time using the second of the provided spot rates, or discount rates, 1.12 to the power of 2, and you could do the same thing with 1.13 13 to the power of 3, so cubed, in respect of the third cash flow. Now let's use the calculator to compute these PVs. I'm not going to use the time value of money function here. I'm just going to take each cash flow as it is and do a division. So let me start recording my calculator. Here we go. So the first cash flow was 9. I typed in 6. 9 divided by 1.06 equals 849. I'm going to be quite detailed here. I'm going to write down 8.491 in fact, to make this as precise as possible. Now the second one is 9 divided by 1.12 squared. That's giving me a result of 7.175. Writing that one down. And for the third one, it's a much bigger cash flow. 109 divided by 1.13 to the power of 3, so I need to press Y to the power of X button followed by 3 equals, and that gives a big whopping 75.542. Now if you sum all of these cash flows, you get, let's see, 8.491 plus 7.175 plus 75.542, well, that's 91.208. Let's write this result down. This should be the value of the bond. This should in fact be the price of the bond, and it is over here corresponding with answer C, which has been rounded to just 2 decimal places. Okay, so that's the price. That should be the price of the bond. Right, what I want us to do now, even though it's not part of the question, is to try and compute the yield to maturity for this instrument. If we know its price, and we know it's all the cash flows it's going to generate in the future, we know how long it's going to be around for, we can calculate the YTM using either the cash flow worksheet, or you can use the TVM function on your calculator. So let's do this using TVM. I'm going to clear the TVM by pressing second followed by FV, and now I've still got my 91.208 displayed. I'm going to turn this into my PV, so I'm going to stick a plus minus in front of it so as to make the PV equal minus 91.208, and I do this, I pressed minus already, I stuck the minus in front, I'm now pressing PV. Okay, good. What else? I need an N of 3, so 3 followed by N. I need to tell the calculator that FV equals 100, so 100 followed by FV, and I need to tell the calculator what the PMT is. PMT is going to be, in this case, 9, so 9 followed by PMT. Good. And now I can get my calculator to compute I over Y. Let's see, compute I over Y, and it tells me 12.705. So in the exam you may actually be given a series of spot rates and either just ask to compute the price of the bond, okay, or actually go one step further and compute the yield to maturity on the bond, which is what I did here, even though it wasn't part of the question. Please appreciate that this yield to maturity kind of is quite close to the final of these last of these spot rates, because you'll see that the YTM is effectively a single discount rate that we can use to discount all the cash flows that will generate the same PV. So it has to be some kind of average, but it's weighted by the size of the payments, because the biggest payments comes typically at the end of the bond's life. The YTM will be pulled towards that final discount rate, or the final spot rate, 13%. Okay, so what I want to do now to show you how the YTM on a bond actually works, I want to recreate the same computation that we did just a moment ago. So take all those cash flows that we had, but this time use the YTM to perform the discounting. Okay, let's draw the timeline again. Okay, maybe let's move this to the right a little bit, and I'm going to have my cash flows 9, 9, and 109 over here, and I'm going to discount to I guess over here times 0. So this is times 0, end of year 1, end of year 2, end of year 3, but this time for the discounting I'm going to use a single rate equal to the YTM. So I'll divide this by 1.12705. Yeah, I got that, 1.12705, good. I'm going to do the second one by discounting by a factor of 1.12705 to the power of 2, and do the same over here, but this time cube that factor. So let's see what we get. Cleared the workings, cleared what was on my display. 9 divided by 1.12705. Okay, got that one wrong. Let's correct this. 705. That's better. 7.985. Once again, I will be quite. Have to be careful here. 7.985. I'm doing this, to 3 decimal places to get as close to the result as I can, realistically. Then I'll do 9 divided by 1.12705 to the power of 2 equals 7.085. And finally, the last cash flow, 109 divided by 1.12705 to the power of 3. Okay, 76.137. Now, if you add all of these, 7.985 plus 7.085 plus 76.137, you'll get a sum of 91.207. And please appreciate that even though we had, well, hopefully you can see this right now, yeah, just about, let's make the screen a little bit smaller. When discounting with individual spot rates, we got distinct PVs for every cash flow, and the PVs we got now when discounting with the YTM were, well, each one was different to their respective, to the PV for that cash flow when using the specific spot rate. So we've got, sorry, try again. My computer wants to very much correct my shape drawing here. The individual P present values for the specific cash flows from the bond are absolutely different than the ones I highlighted in yellow just a moment ago. But please note that the sum is the same, or almost the same. We had 91.208 here and 91.207. So hopefully this gets you to appreciate, allows you to appreciate what the YTM, the yield to maturity, actually is. It's a single discount rate that we can apply to all the cash flows which the bond will generate in the future, and which, once we apply it, allows us to arrive at its current market price. And you can arrive at that price by either discounting all the cash flows using the YTM, the yield to maturity, or performing the discounting on the basis of individual spot rates. Okay, so that's enough for this lesson. See you in the next one.